File Allocation Table is the name of a computer file system architecture and a family of industry-standard file systems utilizing it. The FAT file system is a legacy file system which is simple and robust. It offers good performance even in lightweight implementations, but cannot deliver the same performance, reliability and scalability as some modern file systems. It is, however, supported for compatibility reasons by nearly all currently developed operating systems for personal computers and many mobile devices and embedded systems, and thus is a well-suited format for data exchange between computers and devices of almost any type and age from 1981 up to the present. Originally designed in 1977 for use on floppy disks, FAT was soon adapted and used almost universally on hard disks throughout the DOS and Windows 9X eras for 2 decades. As disk drives evolved, the capabilities of the file system have been extended accordingly, resulting in 3 major file system variants: FAT12, FAT16 and FAT32. The FAT standard has also been expanded in other ways while generally preserving backward compatibility with existing software. With the introduction of more powerful computers and operating systems, as well as the development of more complex file systems for them, FAT is no longer the default file system for usage on Microsoft Windows computers. Today, FAT file systems are still commonly found on floppy disks, USB sticks, flash and other solid-state memory cards and modules, and many portable and embedded devices. Dcf implements FAT as the standard file system for digital cameras. FAT is also utilized in the boot stage of EFI-compliant computers. Overview, Concepts. The name of the file system originates from the file system's prominent usage of an index table, the file allocation table, statically allocated at the time of formatting. The table contains entries for each cluster, a contiguous area of disk storage. Each entry contains either the number of the next cluster in the file, or else a marker indicating end of file, unused disk space, or special reserved areas of the disk. The root directory of the disk contains the number of the first cluster of each file in that directory. The operating system can then traverse the FAT table, looking up the cluster number of each successive part of the disk file as a cluster chain until the end of the file is reached. In much the same way, subdirectories are implemented as special files containing the directory entries of their respective files. Originally designed as an 8-bit file system, the maximum number of clusters has been significantly increased as disk drives have evolved, and so the number of bits used to identify each cluster has grown. The successive major variants of the FAT format are named after the number of table element bits, 12, 16, and 32. Except for the original 8-bit FAT precursor, each of these variants is still in use. The FAT standard has also been expanded in other ways while generally preserving backward compatibility with existing software. Uses. The FAT file system has a long history of usage on desktops and portable computers, and it is frequently used in embedded solutions. FAT offers reasonably good performance and robustness, even in very lightweight implementations. It is therefore widely adopted and supported by virtually all existing operating systems for personal computers as well as some home computers and a multitude of embedded systems. As such, it continues to be the most widespread file system worldwide. This also makes it a useful format for solid-state memory cards and a convenient way to share data between operating systems. FAT file systems are the default file system for removable media and as such are commonly found on floppy disks, super floppies, memory and flash memory cards or USB flash drives and are supported by most portable devices such as PDAs, digital cameras, camcorders, media players, or mobile phones. While FAT12 is omnipresent on floppy disks, FAT16 and FAT32 are typically found on the larger media. FAT was also commonly used on hard disks throughout the DOS and Windows 9X eras, but its use on hard drives has declined since the introduction of Windows XP, which primarily uses the newer NTFS. FAT is still used in hard drives expected to be used by multiple operating systems, such as in shared Windows, Linux and DOS environments. Due to the widespread use of FAT-formatted media, Many operating systems provide support for FAT through official or third-party file system handlers. For example, OS/2, Linux, FreeBSD and BOS provide inbuilt support for FAT, even though they also support more sophisticated file systems such as Exfat or Btrfs. Mac OS 9 and Mac OS X support FAT file systems on volumes other than the boot disk. Amiga OS supports FAT through the Cross-DOS package. For many purposes, the NTFS file system is superior to FAT in terms of features and reliability. Its main drawbacks are its complexity and a size overhead for small volumes, as well as the very limited support by anything other than the NT-based versions of Windows, since the exact specification is a trade secret of Microsoft. The availability of NTFS 3G since mid-2006 has led to much improved NTFS support in Unix-like operating systems, considerably alleviating this concern. It is still not possible to use NTFS in DOS-like operating systems without third-party drivers, which in turn makes it difficult to use a DOS floppy for recovery purposes. Microsoft provided a recovery console to work around this issue, but for security reasons it severely limited what could be done through the recovery console by default. The movement of recovery utilities to boot CDs based on BART-PE, Linux, or WinPE is eroding this drawback, but the NTFS's complexity forbids its implementation in lightweight operating systems and embedded systems. The Dcf file system adopted by almost all digital cameras since 1998 defines a logical file system with 8.3 filenames and makes the usage of either FAT12, FAT16, FAT32 or Exfat mandatory for its physical layer in order to maximize platform interoperability. FAT is also utilized internally for the EFI system partition in the boot stage of EFI-compliant computers. For floppy disks, FAT has been standardized as ECMA 107 and ISO IECA 9293-1994. These standards cover FAT12 and FAT16 with only short 8.3 filename support. Long filenames with VFAT are partially patented. Nomenclature: technically, the term FAT file system refers to all three major variants of the file system, FAT12, FAT16 and FAT32, and most parties clearly distinguish between them where necessary. In contrast to this, Microsoft typically no longer distinguishes between all three of them since the introduction of FAT32, and refers to both FAT12 and FAT16 as FAT, whereas FAT32 gets treated specially in dialog boxes and documentation. This can sometimes lead to confusion if the actual type of the file system used is not mentioned or cannot be explicitly specified. Another common cause of confusion exists within the group of FAT16 file systems, since the term FAT16 refers to both either the whole group of FAT file systems with 16-bit wide cluster entries, or specifically only the original implementation of it with 16-bit sector entries, when it becomes necessary to differentiate between the original and the later implementation. While technically the newer variant with 32-bit sector entries is called FAT16B, it is commonly referred to under the name FAT16 as well, in particular since the original variant is rarely seen today and typically only used on small media when backward compatibility with DOS before 3.31 is required. Further, the term VFAT has led to various misconceptions as well, as it is sometimes erroneously used as if it would describe another variant of FAT file system to be distinguished from the FAT12, FAT16 and FAT32 file systems, while in reality it does not specify another file system, but an optional extension, which can work on top of any FAT file system, FAT12, FAT16 or FAT32. Volumes utilizing VFAT long file names can be read also by operating systems not supporting the VFAT extension, for as long as they support the underlying file system. Yet another cause for misconception stems from some apparent redundancy and possible ambiguity in the definition of FAT volumes. The general type of file system is determined by the width of the cluster entries in the FAT. Specific threshold values for the amount of clusters have been defined to determine which FAT type is used. Even though other properties such as the size of the volume, the count of sectors, the BPB format, the file system name in an eBPB, or in case of partitioned media the used partition ID may often seem to be well-suited distinguishing criteria as well, they cannot reliably be used to derive the file system type from in all scenarios. Whilst uncommon, it is technically possible to define an FAT12 or FAT16 volume using a FAT32 eBPB, which is normally used for FAT32 volumes, only. Also, while partition IDs sometimes indicate special properties such as hidden, secure, CHS or LBA access to an operating system, and as such are often used in conjunction with particular file system variants only, they are typically not used to specify a type of file system by themselves, but rather to keep operating systems not aware of a partition ID from accessing partitions they cannot handle or should not work with. It is therefore necessary to distinguish generic FAT file system types such as FAT12, FAT16 or FAT32 from FAT partition types such as FAT12, FAT16, FAT16B, FAT16X, FAT32, FAT32X etc. In order to be technically correct and exact, this article uses standard prefixes for the byte unit. 1000 bytes are 1 KB and 1024 bytes equal 1 KIB etc. Types. Original 8-bit FAT. The original FAT file system was designed and coded by Mark MacDonald, based on a series of discussions between MacDonald and Bill Gates. It was introduced with 8-bit table elements in a precursor to Microsoft's standalone disk BASIC 80 for an 8080-based successor of the NCR 7200 Model 6 data entry terminal, equipped with 8-inch floppy disks, in 1977/1978. In 1978, standalone disk BASIC 80 was ported to the 8086 using an emulator on a DECP DP10. Since no real 8086 systems were available at this time. The FAT file system was also utilized in Microsoft's MDOS Midas, an operating system for 8080/Z80 platforms written by MacDonald since 1979. The standalone disk BASIC version supported 3 FATs, whereas this was a parameter for Midas. Reportedly, Midas was also prepared to support 10-bit, 12-bit and 16-bit FAT variants. While the size of directory entries was 16 bytes in standalone disk BASIC, Midas instead occupied 32 bytes per entry. Tim Paterson of Seattle Computer Products was first introduced to Microsoft's FAT structure when he helped Bob O'Rear adapting the standalone disk BASIC 86 emulator port onto SCP's S100 bus 8086 CPU board prototype during a guest week at Microsoft in May 1979. The final product was shown at Lifeboat Associates booth stand at the National Computer Conference in New York on June 7, 1979, where Paterson learned about the more sophisticated FAT implementation in MDOS Midas and MacDonald talked to him about the design of the file system. FAT12, between April and August 1980, while borrowing the FAT concept for SCP's own 8086 operating system QDOS 0.10, Tim Paterson extended the table elements to 12 bits, reduced the number of FATs to 2, redefined the semantics of some of the reserved cluster values, and modified the disk layout, so that the root directory was now located between the FAT and the data area for his implementation of FAT12. Paterson also increased the 9-character file name length limit to 11 characters in order to support CP/M-style 8.3 file names and file control blocks. The format used in Microsoft standalone disk BASIC's 8-bit file system precursor was not supported by QDOS. By August 1980, QDOS had been renamed into 86DOS already. Starting with 86DOS 0.42, the size and layout of directory entries was changed from 16 bytes to 32 bytes in order to add a file date stamp and increase the theoretical file size limit beyond the previous limit of 16 MB. 86DOS 1.00 became available in early 1981. Later in 1981, 86DOS evolved into Microsoft's MS-DOS and IBM PC-DOS. The capability to read previously formatted volumes with 16-byte directory entries was dropped with MS-DOS 1.20. Originally designed as a file system for floppy disks, FAT12 used 12-bit entries for the cluster addresses in the FAT, which not only limited the maximum generally possible count of data clusters to 4078 or in some controlled scenarios even up to 4084, but made FAT manipulation tricky with the PC's 8-bit and 16-bit registers. The disk size was stored and calculated as a 16-bit count of sectors, which limited the size to 32 MB for a logical sector size of 512 bytes. FAT12 was used by several manufacturers with different physical formats, but a typical floppy disk at the time was 5.25-inch, single-sided, 40 tracks, with 8 sectors per track, resulting in a capacity of 160 KB for both the system areas and files. The FAT12 limitations exceeded this capacity by a factor of 10 or more. By convention, all the control structures were organized to fit inside the first track, thus avoiding head movement during read and write operations, although this varied depending on the manufacturer and physical format of the disk. A limitation which was not addressed until much later was that any bad sector in the control structure's area, track or 0, could prevent the disk from being usable. The DOS formatting tool rejected such disks completely. Bad sectors were allowed only in the file data area and were marked with the reserved value 0xFF7 in the FAT. They made the entire containing cluster unusable. While 86DOS supported 3-disk formats on 8-inch floppy drives, IBM PCA DOS 1.0, released with the original IBM personal computer in 1981, supported only an 8-sector floppy format with a formatted capacity of 160 KB for single-sided 5.25-inch floppy drives, and PCA DOS 1.1 added support for a double-sided format with 320 KB. PC DOS 2.0 introduced support for 9-sector floppy formats with 180 KB and 360 KB. 86DOS 1.00 and PCA DOS 1.0 directory entries included only one date, the last modified date. PCA DOS 1.1 added the last modified time. PCA DOS 1X file attributes included a hidden bit and system bit, with the remaining 6 bits undefined. At this time, DOS did not support a hierarchical file system, which was still acceptable, given that the number of files on a disk was typically not more than a few dozen. The PC-XT was the first PC with a hard drive from IBM, and PCA DOS 2.0 supported that hard drive with FAT12. The fixed assumption of 8 sectors per clusters on hard disks practically limited the maximum partition size to 16 MB for 512-byte sectors and 4 KB clusters. The BIOS parameter block was introduced with PCA DOS 2.0 as well, and this version also added read-only, archive, volume label, and directory attribute bits for hierarchical subdirectories. MS-DOS 3.0 introduced support for high-density 1.2 MB 5.25-inch diskettes, which notably had 15 sectors per track, hence more space for the FATs. FAT12 remains in use on all common floppy disks, including 1.44 MB and later 2.88 MB disks. Initial FAT16, on August 14, 1984, IBM released the PC-AT, which featured a 20 MB hard disk and PC DOS 3.0. Microsoft introduced MS-DOS 3.0 in parallel. Cluster addresses were increased to 16-bit, allowing for up to 65,524 clusters per volume, and consequently much greater file system sizes, at least in theory. However, the maximum possible number of sectors and the maximum size of 32 MB did not change. Therefore, although cluster addresses were 16 bits, this format was not what today is commonly understood as FAT16. A partition type 0x04 indicates this form of FAT16 with less than 65,536 sectors. With the initial implementation of FAT16 not actually providing for larger partition sizes than FAT12, The early benefit of FAT16 was to enable the use of smaller clusters, making disk usage more efficient, particularly for large numbers of files only a few hundred bytes in size. MS-DOS 2X hard disks larger than 15 MB are incompatible with later versions of MS-DOS. A 20 MB hard disk formatted under MS-DOS 3.0 was not accessible by the older MS-DOS 2.0 because MS-DOS 2.0 did not support version 3.0's FAT16. MS-DOS 3.0 could still access MS-DOS 2.0 style 8 to KIB cluster partitions under 15 MB. Logical sectored FAT. When hard disks grew larger and the FAT12 and FAT16 file system implementation in MS-DOS/PCA-DOS did not provide means to take advantage of the extra storage, several manufacturers developed their own FAT variants to address the problem in their MS-DOS OEM issues. Some vendors supported 8, instead of the standard 4, primary partition entries in their custom extended master boot record, and they adapted MS-DOS to use more than a single primary partition. Other vendors worked around the volume size limits imposed by the 16-bit sector entries and arithmetics by increasing the size of the sectors the file system dealt with, thereby blowing up dimensions. These so-called logical sectors were larger than the physical sector size as expected by the RAM BIOS INT13 hours or the disk drive hardware. The DOS BIOS or system BIOS would then combine multiple physical sectors into logical sectors for the file system to work with. These changes were transparent to the file system implementation in the DOS kernel, since on the file system's abstraction level volumes are seen as a linear series of logically addressable sectors, also known as absolute sectors, starting with LSNA0, independent of the physical location of the volume on the physical medium and its geometry. The underlying DOS BIOS translated these logical sectors into physical sectors according to partitioning information and the drive's physical geometry. The drawback of this approach was a less memory-efficient sector buffering and deblocking in the DOS BIOS, thereby causing an increased memory footprint for the DOS data structures. Since older DOS versions were not flexible enough to work with these logical geometries, the OEMs had to introduce new partition IDs for their FAT variants in order to hide them from off-the-shelf issues of MS-DOS and PC-DOS. Known partition IDs for logical sectored FATs include 0x08, 0x11, 0x14, 0x24, 0x56, 0xe5, 0xf2. OEM versions like Toshiba MS-DOS, Wise MS-DOS 3.2 and 3.3, as well as Zenith MS-DOS are also known to have utilized logical sectoring. While non-standard and suboptimal, these FAT variants are perfectly valid according to the specifications of the file system itself. Therefore, even if default issues of MS-DOS and PC-DOS were not able to cope with them, most of these vendor-specific FAT12 and FAT16 variants can be mounted by more flexible file system implementations in operating systems such as Drive DOS, simply by changing the partition ID to one of the recognized types. Also, if they no longer need to be recognized by their original operating systems, existing partitions can be converted into FAT12 and FAT16 volumes more compliant with versions of MS-DOS PCA-DOS 4.0-6.3, which do not support sector sizes different from 512 bytes, by switching to a BPB with 32-bit entry for the number of sectors, as introduced since DOS 3.31, keeping the cluster size and reducing the logical sector size in the BPB down to 512 bytes, while at the same time increasing the counts of logical sectors per cluster, reserved logical sectors, total logical sectors, and logical sectors per FAT by the same factor. A parallel development in MS-DOS/PC-DOS which allowed an increase in the maximum possible FAT size was the introduction of multiple FAT partitions on a hard disk. To allow the use of more FAT partitions in a compatible way, a new partition type was introduced in PCA-DOS 3.2, the extended partition, which is a container for an additional partition called logical drive. Since PCA-DOS 3.3, there is another, optional extended partition containing the next logical drive, and so on. The MBR of a hard disk can either define up to 4 primary partitions, or an extended partition in addition to up to 3 primary partitions. Final FAT16, in November 1987, Compaq MS-DOS 3.31 introduced what today is simply known as the FAT16 format, with the expansion of the 16-bit disk sector count to 32 bits in the BPB. Although the on-disk changes were minor, the entire DOS disk driver had to be converted to use 32-bit sector numbers, a task complicated by the fact that it was written in 16-bit assembly language. The result was initially called the DOS 3.31 Large File System. Microsoft's DSKPROBE tool refers to Type 0x06 as Big Fat, whereas some older versions of FDISK described it as Big DOS. Technically, it is known as FAT16B. Since older versions of DOS were not designed to cope with more than 65,535 sectors, it was necessary to introduce a new partition type for this format in order to hide it from pre-3.31 issues of DOS. The original form of FAT16 had a partition type 0x04. To deal with disks larger than this, type 0x06 was introduced to indicate 65,536 or more sectors. In addition to this, the disk driver was expanded to cope with more than 65,535 sectors as well. The only other difference between the original FAT16 and the newer FAT16B format is the usage of a newer BPB format with 32-bit sector entry. Therefore, newer operating systems supporting the FAT16B format can cope also with the original FAT16 format without any necessary changes. If partitions to be used by pre-DOS 3.31 issues of DOS need to be created by modern tools, the only criteria theoretically necessary to meet are a sector count of less than 65,536, and the usage of the old partition ID. In practice, however, Type 0x01 and 0x04 primary partitions should not be physically located outside the first 32 MB of the disk, due to other restrictions in MS-DOS 2X, which could not cope with them otherwise. In 1988, the FAT16B improvement became more generally available through DRDISA 3.31, PCA DISA 4.0, OS/2A 1.1, and MS-DOS 4.0. The limit on partition size was dictated by the 8-bit signed count of sectors per cluster, which originally had a maximum power of 2 value of 64. With the standard hard disk sector size of 512 bytes, this gives a maximum of 32 KB cluster size, thereby fixing the definitive limit for the FAT16 partition size at 2 GB for sector size 512. On magneto-optical media, which can have 1 or 2 KB sectors instead of 0.5 KB, this size limit is proportionally larger. Much later, Windows NT increased the maximum cluster size to 64 KB, by considering the sectors per cluster count as unsigned. However, the resulting format was not compatible with any other FAT implementation of the time, and it generated greater internal fragmentation. Windows 98, SE and ME also supported reading and writing this variant, but its disk utilities did not work with it and some FCB services are not available for such volumes. This contributes to a confusing compatibility situation. Prior to 1995, versions of DOS accessed the disk via CHS addressing only. When MIS-DOS 7.0/Windows 95 introduced LBA disk access, partitions could start being physically located outside the first circa 8 GB of this disk and thereby out of the reach of the traditional CHS addressing scheme. Partitions partially or fully located beyond the CHS barrier therefore had to be hidden from non-LBA-enabled operating systems by using the new partition type 0xoe in the partition table instead. FAT16 partitions using this partition type are also named FAT16X. The only difference, compared to previous FAT16 partitions, is the fact that some CHS-related geometry entries in the BPB record, namely the number of sectors per track and the number of heads, may contain no or misleading values and should not be used. The number of root directory entries available for FAT12 and FAT16 is determined when the volume is formatted, and is stored in a 16-bit field. For a given number RDE in sector size SS, the number RDS of root directory sectors is RDS equals CL RDEA, 32/SS, and RDE is normally chosen to fill these sectors, that is, RDE 32 equals RDSSS. FAT12 and FAT16 media typically use 512 root directory entries on non-floppy media. Some third-party tools, like NCDOSFs, allow the user to set this parameter. FAT32, in order to overcome the volume size limit of FAT16, while at the same time allowing DOS real mode code to handle the format, Microsoft designed a new version of the file system, FAT32, which supported an increased number of possible clusters, but could reuse most of the existing code, so that the available conventional memory footprint was reduced by less than 5 KB under DOS. Cluster values are represented by 32-bit numbers, of which 28 bits are used to hold the cluster number. The boot sector uses a 32-bit field for the sector count, limiting the FAT32 volume size to 2 TB for a sector size of 512 bytes and 16 TB for a sector size of 4096 bytes. FAT32 was introduced with MISTOS 7.1/Windows 95 OS 2 in 1996, although reformatting was needed to use it, and Drive Space 3 never supported it. Windows 98 introduced a utility to convert existing hard disks from FAT16 to FAT32 without loss of data. In the Windows NT line, native support for FAT32 arrived in Windows 2000. A free FAT32 driver for Windows NT 4.0 was available from Internals, a company later acquired by Microsoft. Since the acquisition, the driver is no longer officially available. Since 1998, Caldera's dynamically loadable DR FAT32 driver could be used to enable FAT32 support in Drive DOS. The first version of Drive DOS to natively support FAT32 and LBA access was OEM Drive DOS 7.04 in 1999. That same year, IMS introduced native FAT32 support with Real/32A 7.90, and IBM 4690 OS added FAT32 support with version 2. Ahead Software provided another dynamically loadable FAT32EXE driver for Drive DOS 7.03 with narrow burning ROM in 2004. IBM PCA DOS introduced native FAT32 support with OEM PCA DOS 7.10 in 2003. The maximum possible size for a file on a FAT32 volume is 4 GB-1 byte or 4,294,967,295 bytes. This limit is a consequence of the file length entry in the directory table and would also affect huge FAT16 partitions with a sufficient sector size. Video applications, DVD images, large databases, and some other software easily exceed this limit. The OpenFAT Plus specification proposes how to store larger files up to 256 GB-1 byte or 274,877,906,943 bytes on slightly modified and otherwise backwards compatible FAT32 volumes, but imposes a risk that disk tools or FAT32 implementations not aware of this extension may truncate or delete files exceeding the normal FAT32 file size limit. Also, support for FAT32 Plus is limited to some versions of Drive DOS and not available in mainstream operating systems so far. As with previous file systems, the design of the FAT32 file system does not include direct built-in support for long file names, but FAT32 volumes can optionally hold VFAT long file names in addition to short file names in exactly the same way as VFAT long file names have been optionally implemented for FAT12 and FAT16 volumes. Two partition types have been reserved for FAT32 partitions, 0xob and 0xoc. The latter type is also named FAT32X in order to indicate usage of LBA disk access instead of CHS. On such partitions, Some CHS-related geometry entries in the EBPB record, namely the number of sectors per track and the number of heads, may contain no or misleading values and should not be used. Extensions, extended attributes. OS/2 heavily depends on extended attributes and stores them in a hidden file called idata.sf in the root directory of the FAT12 or FAT16 volume. This file is indexed by 2 previously reserved bytes in the files directory entry at offset 0x14. In the FAT32 format, these bytes hold the upper 16 bits of the starting cluster number of the file or directory, hence making it impossible to store OS/2 EAs on FAT32 using this method. However, the third-party FAT32 installable file system driver FAT32 IFS version 0.70 and higher by Henkelder and NetLabs for OS/2 and Ecom Station stores extended attributes in extra files with file names having the string EA/SF appended to the regular file name of the file to which they belong. The driver also utilizes the byte at offset 0xoc in directory entries to store a special mark byte indicating the presence of extended attributes to help speed up things. Extended attributes are accessible via the Workplace Shell desktop, through REXX scripts, and many system GUI and command line utilities. To accommodate its OS/2 subsystem, Windows NT supports the handling of extended attributes in HPFS, NTFS, FAT12 and FAT16. It stores EAs on FAT12, FAT16 and HPFS using exactly the same scheme as OS/2, but does not support any other kind of ADS as held on NTFS volumes. Trying to copy a file with any ADS other than EAs from an NTFS volume to a FAT or HPFS volume gives a warning message with the names of the ADSs that will be lost. It does not support the FAT32 IFS method to store EAs on FAT32 volumes. Windows 2000 onward acts exactly as Windows NT, except that it ignores EAs when copying to FAT32 without any warning. Cygwin uses idata.sf files as well. Long file names. One of the user experience goals for the designers of Windows 95 was the ability to use long file names, in addition to classic 8.3 file names. For backward and forward compatibility, LFNs were implemented as an optional extension on top of the existing FAT file system structures using a workaround in the way directory entries are laid out. This transparent method to store long file names in the existing FAT file systems without altering their data structures is usually known as VFAT after the Windows 95 Virtual Device Driver. Non-VFAT-enabled operating systems can still access the files under their short file name alias without restrictions, however, the associated long file names may get lost when files with long file names are copied under non-VFAT-aware operating systems. In Windows NT, support for VFAT long file names started from version 3.5. Linux provides a VFAT file system driver to work with FAT volumes with VFAT long file names. For some while, a UVFAT driver was available to provide combined support for MS-DOS-style permissions with VFAT long file names. OS/2 added long file name support to FAT using extended attributes before the introduction of VFAT. Thus, VFAT long file names are invisible to OS/2, and EA long file names are invisible to Windows, therefore experienced users of both operating systems would have to manually rename the files. In order to support Java applications, the FlexOS-based IBM 4690 OS version 2 introduced its own virtual file system architecture to store long file names in the FAT file system in a backwards compatible fashion. If enabled, the virtual file names are available under separate logical drive letters, whereas the real file names remain available under the original drive letters. Forks and alternate data streams. The FAT file system itself is not designed for supporting alternate data streams, but some operating systems that heavily depend on them have devised various methods for handling them in FAT drives. Such methods either store the additional information in extra files and directories, or give new semantics to previously unused fields of the FAT on disk data structures. macOS using PC Exchange stores its various dates, file attributes and long file names in a hidden file called finder.dat, and resource forks in a subdirectory called resource.frk, in every directory where they are used. From PC Exchanger 2.1 onwards, they store the macOS long file names as standard FAT long file names and convert FAT file names longer than 31 characters to unique 31-character file names, which can then be made visible to Macintosh applications. macOS X stores resource forks and metadata in a hidden file with a name constructed from the owner file name prefixed with. And Finder stores some folder and file metadata in a hidden file called dsstore. UMSDOS permissions and file names. Early Linux distributions also supported a format known as UMSDOS, a FAT variant with Unix file attributes stored in a separate file called Linux. UMSDOS fell into disuse after VFAT was released and it is not enabled by default in Linux kernels from version 2.5.7 onwards. For some time, Linux also provided combined support for UMSDOS-style permissions and VFAT long file names through UVFAT, derivatives, TurboFat. In its NetWare file system, Novell implemented a heavily modified variant of a FAT file system for the NetWare operating system. For larger files it utilized a performance feature named TurboFat. FATX is a family of file systems designed for Microsoft's Xbox video game console hard disk drives and memory cards, introduced in 2001. While resembling the same basic design ideas as FAT16 and FAT32, the FATX16 and FATX32 on-disk structures are simplified but fundamentally incompatible with normal FAT16 and FAT32 file systems, making it impossible for normal FAT file system drivers to mount such volumes. The non-bootable superblock sector is 4 KB in size and holds an 18-byte large BPB-like structure completely different from normal BPBs. Clusters are typically 16 KB in size and there is only one copy of the FAT on the Xbox. Directory entries are 64 bytes in size instead of the normal 32 bytes. Files can have file names up to 42 characters long using the OEM character set and be up to 4 GB-1 byte in size. The on-disk timestamps hold creation, modification and access dates and times but differ from FAT. In FAT, the epoch is 1980. In FATX, the epoch is 2000. On the Xbox A360, the epoch is 1980. Exfat. Exfat is a file system introduced with Windows Embedded CE 6.0 in November 2006 and brought to the Windows NT family with Vista Service Pack 1. It is loosely based on the file allocation table architecture, but incompatible, proprietary and protected by patents. Microsoft's GUI and command line format utilities offer it as an alternative to NTFS. Exfat is intended for use on flash drives, where FAT32 is otherwise used. Storage devices formatted as Exfat cannot exchange data with equipment not supporting the format. Most consumer electronics do not support Exfat, which requires acquisition of a commercial license from Microsoft, which rules out its legal distribution as part of open-source operating systems. Exfat offers several benefits over FAT32 including breaking the 4 GB file size limit of standard FAT32, being more space efficient for files smaller than 64 KB on large volumes and, compared to lightweight implementations of FAT32 and DOS and some embedded systems, it can offer faster seeks if more than a few thousand files are stored in a single subdirectory, whereas FAT32 is typically faster than Exfat for larger and unfragmented files as used on digital cameras, camcorders and media players or when flashcards are used mainly for archival purposes. The MBR partition type is 0x07. Logical geometry information located in the VBR is stored in a format not resembling any kind of BPB. Patents, Microsoft applied for, and was granted, a series of patents for key parts of the FAT file system in the mid-1990s. All four pertain to long file name extensions to FAT first seen in Windows 95, U.S. Patent 5,579,517, U.S. Patent 5,745,902, U.S. Patent 5,758,352, U.S. Patent 6,286,013. On December 3, 2003, Microsoft announced that it would be offering licenses for use of its FAT specification and associated intellectual property, at the cost of a 25 cents royalty per unit sold, with a $250,000 maximum royalty per license agreement. To this end, Microsoft cited 4 patents on the FAT file system as the basis of its intellectual property claims. In the EFI FAT32 specification, Microsoft specifically grants a number of rights, which many readers have interpreted as permitting operating system vendors to implement FAT. Non-Microsoft patents affecting FAT include U.S. Patent 5,367,671, specific to the OS/2 extended object attributes. Challenges and lawsuits. The Public Patent Foundation submitted evidence to the U.S. Patent and Trade Office in 2004 disputing the validity of U.S. Patent 5,579,517, including prior art references from Xerox and IBM. The USPTO opened an investigation and concluded by rejecting all claims. The next year, the USPTO further announced that following the re-examination process, it affirmed the rejection of 517 and additionally found U.S. Patent 5,758,352 invalid on the grounds that the patent had incorrect assignees. However, in 2006 the USPTO ruled that features of Microsoft's implementation of the FAT system were novel and non-obvious, reversing both earlier decisions and leaving the patents valid. In February 2009, Microsoft filed a patent infringement lawsuit against TomTom alleging that the device maker's products infringe on patents related to VFAT long file names. As some TomTom products are based on Linux, this marked the first time that Microsoft tried to enforce its patents against the Linux platform. The lawsuit was settled out of court the following month with an agreement that Microsoft be given access to 4 of TomTom's patents, that TomTom will drop support for the VFAT long file names from its products, and that in return Microsoft not seek legal action against TomTom for the 5-year duration of the settlement agreement. In October 2010, Microsoft filed a patent infringement lawsuit against Motorola alleging several patents were not licensed for use in the Android operating system. They also submitted a complaint to the ITC. Developers of open-source software have designed methods intended to circumvent Microsoft's patents. In 2013, patentee P0618540 common namespace for long and short file names was invalidated in Germany. See also, comparison of file systems, drive letter assignment, list of file systems, transaction-safe FAT file system, design of the FAT file system, notes. ABA driver named VFAT appeared before Windows 95, in Windows for Workgroups 3.11, but this older version was only used for implementing 32-bit file access and did not support long file names. Windows XP has been observed to create similar hybrid disks when reformatting FAT16B formatted ZIP100 disks to FAT32 format. The resulting volumes were FAT32 by format, but still used the FAT16B EBPB. AB sources differ in regard to the first NCR data entry terminal integrating support for the FAT file system. According to Stephen Mains and Paul Andrews, Gates, development was for a NCR 8200 in late 1977, incorrectly classified as a floppy-based upgrade to the NCR 7200. Which had been released in 1975 November and was built around an Intel 8088-bit processor, but was cassette-based only. However, the NCR Century 8200 was a 16-bit mini-computer, onto which several data entry terminals could be hooked up. Mark MacDonald even remembered an NCR 8500, a mainframe of the Criterion series, which can be ruled out as well. Announced 1977-10 for shipment in 1978 February, NCR also introduced the NCR i80-100 series including the 8080-based NCR i80-130 and NCR i80-150 models of small business systems featuring dual floppy disks. Other sources indicate that either the NCR 7200 series itself or the successor series were the actual target platform. NCR Basic Plus 6 became available for the cassette-based NCR 7200 Model 6 in Q1/1977. The NCR 7500 series was released in 1978, based on a similar 8080 hardware, but now including NCR 7520 and 7530 models featuring 8-inch diskettes. NCR Basic Plus 6, a precursor or adaptation of standalone disk Basic 80, was available for them at least since 1979. One source claims that a special NCR 7200 model variant with two 8-inch diskettes and Microsoft Basic existed and was imported by NCR Sydney into Australia the least. CFAT end-of-chain marker for special precautions in regard to occurrences of a cluster value of 0xFFO on FAT12 volumes under MS-DOS PC DOS 3.3 and higher. Dr. DOS is able to boot off FAT12/FAT16 logical sectored media with logical sector sizes up to 1024 bytes. References. External links, description of the FAT32 file system, Microsoft Knowledge Base article 154,997 milliseconds DOS, directory and subdirectory limitations, Microsoft Knowledge Base article 39,927, overview of FAT, HPFS, and NTFS file systems, Microsoft Knowledge Base article 100,108, volume and file size limits of FAT file systems, Microsoft TechNet, Microsoft TechNet. A Brief and Incomplete History of FAT32 by Raymond Chen. FDISK does not recognize full size of hard disks larger than 64 GB. Microsoft Knowledge Base. Article 263,044. Microsoft Windows XP, FAT32 file system. Copy made by Internet Archive Wayback Machine of an article with summary of limits in FAT32 which is no longer available on Microsoft website.